Good morning, everyone. Hope that you guys are having a good start to your Tuesday. Nope, nope. We'll go with a good start to your Thursday. I hope that you had a good Tuesday. Um, so what I want to do right now is I'm going to throw our PowerPoint for today onto the Canvas page, and I'm going to send you guys the link for that document, so that if you want to download it and kind of play along, you're more than welcome to. Um, I'll also make it a PDF and post that. So, yeah. Now, this link that you use for today's lecture is the link that we'll use over the course of the entire semester. So that's one good thing that you don't really have to worry about navigating. Um, and I will post this link on our Canvas homepage so that it's persistent and you can always join that one. Now, with that said, what we're going to be getting into today is our first bit of content for this semester. And we're going to be talking about physical and chemical properties. Now, I'm about to add the PDF, then I'm going to give you guys the link. PDF, uploading, and save. We've got 70 folks here. Good morning, Ryan. We got 70 folks in here, and we are going to do a test drive of a poll question just so you guys can see how it works. And I think, these questions are not going to be something that really is, this is like a trial period still, so that you can figure out, if you're using a mobile device, what it looks like, where to expect the questions and answer options. Then if you're using a desktop computer, what you can expect for your uh, responses and where to put those and everything like that. But with that in mind, going to go ahead and start. We'll do the poll questions after a little bit because, I don't want to do it like right now. We'll do it in like 30 minutes or so, just to get the idea that most folks who are going to join the class are here for the day. Okay, so what we are talking about, chemical and physical properties and chemical and physical changes, and we'll get into a little bit of classification or organization of matter. Now, just so you guys have a good understanding of what we're doing this entire semester is, this class, if you look at the description, you might think, or actually, go ahead and add a number to the chat if you have taken a chemistry class before, and a letter in the chat if you have never taken a chemistry class. Okay, so if I had to guess based on those responses, it looks like it's about, just a very rough estimate. Maybe three-quarters of the class has taken a chemistry class before, and then about a quarter has yet to take a chemistry class. Um, what I want this class to be for you guys is I want it to be something where you're like, oh, okay, I'm analyzing something. I'm thinking about the world in terms of chemistry. Right now, I'm drinking a cup of coffee. So we will get into a little bit of like what is in coffee, how is it made, and what is like when you ground up coffee beans and soak them in hot water, what do you get and why do you get that? So we'll talk about those sorts of things. I don't want this to be, I'm gonna write on here. I don't want this to be Gen Chem Light. What I mean by that is I don't want this to be a class where you're like, oh, well, if I were a science major, I'd take general chemistry, but I'm not a science major, so I'm taking this class, which is basically just, we've removed some stuff from general chemistry and we've made it a little bit simpler or something like that. I don't want that to be the perception of this class, and I don't want you to walk away with like, oh yeah, that's what I learned about. I want you guys to walk away from this class and say, okay, well, I know a little bit about dyes and sodas and flavoring agents and stuff like that. So we will get there, but in order to get there, we do have to do a little bit of that Gen Chem light sort of stuff. We have to understand like kind of how the world operates in terms of matter and how it's measured, what it consists of. So we've got to start there, and that's where we're going to start today. So chemical and physical properties are properties that basically everything has. Now, um, for example, there are some things that light on fire when they're exposed to air. And that's what we've got on the left-hand side here. We've got copper, or sorry, not copper. We've got carbon that basically, when exposed to O2, is going to ignite. And then on the right-hand side here, we've got some copper filings. Now, if you were to pick these two different materials up, they're going to have a different texture. They're going to feel different. Now, with that, we've got a physical property. A physical property is a characteristic of a substance that can be observed or measured without changing the identity of the substance. Okay, so what that means is you can basically touch something and you have an understanding of, well, how it is without having to change it. Another rephrasing of that is a physical property is a trait of a substance that can be seen or measured without altering that substance. So that would be something like, I hate to use my coffee cup because it's got coffee in it, but when I tap the side of it, do I learn something about what it consists of? Do I learn a property of it? Could I use that information in another context? And what I mean by that is, well, when I tap the side, one, it makes a noise, but also it kind of hurts my finger. Not hurts, I'm tougher than that. But could I imagine, well, what if this hit my head? Would it hurt me? Potentially. So, with that in mind, can somebody add to the chat a physical property for this aluminum coffee cup? Solid. Yeah. It's hard. Exactly. Perfect. Those are great. It is a solid. That's a physical property that I recognize. In addition to that, if I'm going to describe it to someone, well, I'm going to give people two different options. Hey, I can either throw a styrofoam brick at you, or I can throw a brick that's made of this same material at you. Which do you think they're going to pick? They're probably going to pick the styrofoam brick because they probably don't want to get hurt. Those are both physical properties. The softness of the styrofoam brick versus the, well, hardness of the coffee cup. So that's a physical property. Now, in my investigation to find out that this was hard, did I have to change it at all? No. And what I mean by change it is like, did I have to take it outside? Did I have to expose it to sunlight? Did I have to heat it up at all? No. At room temperature, whenever I hit that coffee mug against my arm or something, I'm like, oh yeah, that is hard. Okay, now also looking at this, is there any other term or are there any other terms that I could use to describe it? Well, this part's white, so the color of something is a physical property. Now, some other examples of physical properties are as follows. And you know what? I made a mistake and I apologize for that. I told you guys that I would send you the link where you could download our PowerPoint or PDF of the notes, and I did not, but I just did Canvas, TX State, and then welcome August. Add a number to the chat if you can see if you followed that link, and yes, it's functional. Great. So I'll take a pause for just a moment so you guys can download that if you want or open it up. I know that some folks like using the PowerPoint just because then they can mark it up and add their notes. Others like using the PDF because it will open in the browser easily. I like to put them both there so you guys have access to those. Okay, now this is slide number 7. Okay, so some physical properties are just simple descriptors. The color of something is a physical property. The hardness is a physical property. Um, does anyone know what malleability means? Add a Y or an N to the chat if you know what malleability is. And I pose that question low stakes because I'm guessing that no one's like, oh, I don't know, but I want to present that. Yes, I do know. Malleability is the bendability. So how flexible something is, basically. One substance that's particularly malleable is gold. Gold is a malleable substance, but it has other properties of um, other metals, or it's classified as a metal because of other properties. An indication that I always think of whenever I think of the malleability of gold is my mother-in-law went to Texas A&M, and so she has an Aggie ring, and over the years that ring has, I don't know if anyone, how familiar anyone is with like a Aggie ring or a class ring. She graduated in the 70s, and you cannot even tell that there was ever a Texas A&M, not plaque, what's the word? Seal on there, just because over the years, she's worn it every day for 50 some odd years, and she'll touch something, and slowly but surely that ring has kind of, it looks like it eroded basically. But the malleability is, I'm going to say bendability. Okay. Then electrical conductivity. Well, does something conduct electricity well? If you were to, if something were to be struck by lightning, would the electric current through that lightning go straight through it, or would it stop there? Um, Density. Uh, Melting point and boiling point. These are all physical properties. There's two that I wanted to talk about specifically, solubility and density. Now, whenever I think of solubility, what I think about, there's two things that come to mind. The first thing or the first substance and solubility that I think of is sand. And I'll say sand versus salt. And I'm going to go ahead and say 1 for sand and 2 for salt. One of these substances is insoluble in water. Which one of those two? Add a 1 for sand or type out sand and then 2 for salt. Insoluble. Great. Everyone's chiming in with 1 or sand. So that means that if you got a cup of water and you added sand to it, well, that water would not do anything to the sand. The sand's going to go into that solution and just sink to the bottom, basically. Now, that is, you say, insoluble in water. Compare that to salt. Salt is going to be soluble in water. Now, another word that can describe something as being soluble is to describe what's taking place, what happens to that substance. Well, it dissolves in water. Now, so this is the first thing or first combination of things that I think about. The second thing that I always think about is whey protein. Whey protein you can get at GNC or Costco or HEB or anything like that. Um, Go ahead and add a Y or an N to the chat if you have ever had any experience with insoluble whey protein. If you have never had Any experience with insoluble whey protein? Great. If you've had experience with whey protein that is insoluble, then that's a frustration. Now, in addition to that, so essentially what this would mean is like, let's say that for whatever reason, whether you're a endurance athlete or not, you're just trying to get more protein into your diet. Let's say that you start consuming more whey protein. You go buy a whey protein isolate and you say, okay, cool. Well, I'm going to drink this. What I'm going to do is a shake in the morning, shake in morning, and then a shake at dinner. Okay, cool. That's a good way that I can add 40 grams of protein to my diet every day. That's awesome. That's going to help me add more calories and help build muscle. Awesome. This is great. Um, Now, what you want is that to be soluble. You want to be able to go in, make that shake, and then drink it and not have any clumps, not have any solids. Now, if you have some of those clumps, it's really unappetizing. If you have insoluble, unappetizing. Now, I'd like you to think about this from this physical property. Think about it from the perspective of, okay, something goes into solution or something does not go into solution. Something is soluble, it goes into solution, or it's insoluble, does not go into solution. I'm going to give you, let's say that we have source A and source B. And I want you to now think about it kind of from a business perspective. Let's say that you know there are people who need to add whey protein or want to add whey protein, add protein to their diet, and you say, you know what, I'm going to start a business. And my business is going to produce whey protein and we're going to sell it. And I've got two companies that I'm going to be sourcing the whey protein from. Okay, can I get a number in the chat if you follow me so far, or a letter if you're in the chat, you're kind of confused about what I'm talking. Okay, great. So you're starting a business. And let's call it standard protein. That sounds official. People like things that sound official. So you got this company called Standard Protein. And you go and you find two different companies that produce whey protein. What you're going to do is you're going to talk to them and you're going to get their protein and then you're going to put the Standard Protein label on it and you're going to sell it. You've got source A and source B. And source A, they say, well, you know what? 100% of our whey protein is soluble. Seems like a pretty good source to go to. And source B says, well, 90% of our protein, our whey protein is going to be soluble. If you want to sell your product to the most people possible, which one are you going to go to? Are you going to go source it from source A or source B? Absolutely. We're going with A. Because let's say that we went to source B. Well, chances are with source A, 100% satisfaction. All your customers are going to be happy. Whereas source B, is everyone going to be happy with the product that you made? No. Some people are going to be like, I was drinking my whey protein and then all of a sudden I got this chunk of powder in there. and it was disgusting. I'm never buying standard protein ever again because of that. So, well, let's say at best you're like 95% of customers were satisfied. So, my point here, what I'd like you to understand and would like you to appreciate is this is a physical property. This is chemistry in action related to, well, if your customers are super happy with your product, what's that going to mean? Dollar sign, dollar sign, dollar sign. If only 95% of your customers are satisfied, we'll go with dollar sign, dollar sign. So this is chemistry related and a physical property related to or connecting to a business and connecting to like the success of a business. Now, of course, there are other aspects to this and other aspects to, starting a business. It's not like, you know, marketing is absolutely a part of it. So, does everyone follow me there? Give me a number in the chat if you follow and a letter in the chat if you're mixed up by something that I said. Okay. So, what I really just wanted to stress was solubility is a physical property. Everything has a physical property, or everything has physical properties. Solubility, just one example of them. Whey protein that you get at the grocery store is, well, a physical property. If something goes into solution, if something dissolves in water, that would be that it's soluble. If something does not dissolve in water, that is an insoluble substance. Now, this isn't to say that soluble is good and insoluble is bad, but in certain cases, soluble is good, insoluble can be bad. In other instances, insoluble can be great. Soluble might be bad. Okay. The next physical property that I wanted to talk about was density. Now, whenever I think of density, for some reason, the things that come to my mind are a masonry brick, so like a brick for building a house, versus the exact same size styrofoam block. Styrofoam block. And I think about that situation of, well, which would you want to be like, which would you prefer to have thrown at you? A masonry brick or a styrofoam brick block of the exact same size? Chances are you'd want to be hit by the styrofoam. If you have to be hit by one of them, the styrofoam, just because the brick is gonna, it's gonna break skin, it's gonna hurt. Nobody's gonna enjoy that. Styrofoam block, on the other hand, would just be like, oh, it just bounced off of me. Okay. Now, in addition to that, physical properties, like these all listed here, they can be quantified. Density and quantification is basically assigning a number to it. Density, these are all measures of density. Now, all of these things, blood, body fat, whole milk, corn oil, mayonnaise, and honey, well, they have densities very similar to or very close to one. Water, and this is a number that I want you guys to remember. Water has a density of 1.00 grams per milliliter. Now, notice this right here. The label for this column is grams per cm cubed or cm3. So, um, I'm pretty proud of my ability to draw. And I'd like you guys to to experience my drawing abilities. Okay. So, if you can imagine an ice cube, visualize that. Visualize an ice cube. If that ice cube on one side was exactly 1 centimeter. Now visualize that. Then it was 1 centimeter tall. Okay, so now we have an ice square basically that's 1 centimeter. And here's where my drawing abilities really take off. I don't know if anyone heard those sound effects. That was not me. That's just my drawing ability. So we've got a cube that is 1 centimeter by 1 centimeter by 1 centimeter. And if you're thinking, this guy really thinks that he's funny, I don't. I know that I am hilarious. So we've got a cube that's 1 centimeter by 1 centimeter by 1 centimeter. We can call this a cubic centimeter. Add a number to the chat if you've ever watched a TV show where there's like an emergency room situation, or maybe like a medical drama, like Grey's Anatomy or something like that. Okay? Or if you've ever been in an emergency room or a hospital, they'll say, I need 1,000 cc's of saline. cc is the same as cubic centimeter. Or that is the same as 1 centimeter cubed. So this is a volume. So 1 centimeter cubed is the same as 1 milliliter. If anyone has like I don't know, like a 20-ounce Dr. Pepper bottle or a can of cola, a can of Diet Coke or something, I'm mentioning the two drinks that I use most often. If you look on the side of that bottle, the let's see, the Dr. Pepper 20-ounce bottle is, I think, 533 milliliters or 533 ml. That is the same as 533 cc, centimeters cubed, cubic centimeters. Okay, so this is a measure of these things. Now, we're going to get more into density a little bit later, but what I want you to take away from this is physical properties. These are all great physical properties. The color of something, hardness, malleability, solubility, electrical conductivity, density, melting point, and boiling point. The melting point and boiling point, I'm guessing that you know the melting point of water in degrees Fahrenheit. If you do, add it to the chat. The melting point of water, well, 212 is the boiling point of water, and melting point of water is going to be, well, actually, the melting point of ice and the boiling point of, or sorry, and the freezing point of water are the same, 32. So you can say, we'll use water, H2O, not really defining the state. But I saw people threw out 212 and 32. Those are kind of the numbers that I was looking for. The boiling point of water, where it goes from a liquid to a gas, is 212. Where it goes from a solid to a liquid is 32. So we're kind of in the right place right there. Now, a chemical property. A chemical property of matter describes its potential to undergo some chemical change or reaction by virtue of its composition, as well as what elements, electrons, and bonding are present to give the potential for that chemical change. To rephrase that, a chemical property indicates its ability of a substance or the substance's ability to undergo a change or reaction due to its composition, including the elements, electrons, and types of bonding present. So a chemical property is something that basically like, well, will it react or does it react? Some examples of chemical properties. Now, these are all terms that I want you to think about with respect to if a chemical change has taken place or if something undergoes or will undergo a chemical change. If something burns, rots, explodes, decomposes, or ferments, then you should think, okay, a chemical change has taken place. Some of these are a little bit easier to wrap your mind around than others. And the important thing is for all of these, when a chemical change has taken place, well, the starting substance, starter, is different than the end substance. Now, what I want you to think about with respect to that is let's take, for instance, milk. Let's think of states of matter, solids, liquids, and gases. If you were to get a glass of milk and leave it on your windowsill for a week, and you come back to it, and let's say that it hasn't evaporated, but if you come back to it, are you going to have chunks in that milk? Y or N? Into the chat. Yes. So, would you agree with me that you have solids mixed in that liquid? Add a number in the chat if you agree with that statement. Okay, great. So now let's just pause for a minute. We've got this glass of milk. A week later, we've got chunks, solids in there. We've got a mixture of solids and liquids. Um, is that the same thing effectively as a glass of water with ice cubes in it? Y or N to the chat. Some people said no, and some people said yes. Let me ask you this, and I'll present it in this way. Um, would you drink a glass of, well, would you drink a glass of ice water? I'm gonna leave that as rhetorical as yeah. And some people are, yeah, absolutely, it's hot out. Now, would you, and you're not being compensated or anything for this, um, would you drink a glass of week old milk that has some solids in it? No, because something's different, right? Yeah. Um, Ryan, thank you. Absolutely not. You're absolutely right. You would not. Of course, if someone's like, I'll give you $1 million, then it's like, well, now we're talking. Um, but you wouldn't do that because that milk has curdled. Because you're like, I got some for a million. Yeah, totally. That's whenever I say $1 million, then I'm like, but would I do it for $900,000? Yeah, I probably would. And then I'm like, how much? And I like to stop there because I don't want someone to show up at my front door and be like, I'll give you $278. Will you drink this? And I'm like, oh, I don't know. Is it worth it? It might be. Okay. But we'll keep it at an abstract high number. It probably is not. I agree. Because, then you're sick for a couple of days. Well, milk undergoes a chemical change. That milk has curdled. You know that you kind of made really, really gross cottage cheese. The slide deck, follow that link right there. Um, and we are on slide number 12. The PDF and the PowerPoint are available at that link. Absolutely. So when you do, so we have a chemical change that has taken place. So milk curdling, how does that take place? Well, it's the same starting material, but is because of, and actually, let's take a pause for a minute before I finish that sentence. Um, Add a number to the chat, and we're just going to kind of make like a nice little milk nutrition table. Does milk have sugar? Not necessarily like M&Ms or anything like that, but yeah, milk has sugar. One sugar known as lactose. There are some milks that you can get that are lactose free, but regular off the shelf milk is going to have lactose in it. And now we're thinking about whole milk. Does whole milk have fat? Yeah, absolutely. And it's lots of different fats, so I'll just say yes. Last question, does milk have protein? Yeah. Again, with respect to people wanting to like increase protein into their diet, we'll drink a lot of milk. One of my kids drinks a lot of milk. Um, he eats a bowl of cereal, but then he wants a glass of milk to go alongside it. Um, so anyway, when it comes to your like major macronutrients, the ones that help your body like grow and continue to like extract energy and run and do activities, well, milk has a lot of them. It's got sugar, fats, and proteins. Now, with that said, when milk curdles, that is the result of proteins changing. Those proteins they'll do something like proteins have a specific shape, but then under the right circumstances, they'll unfold and they'll take on a different shape. So milk curdling is because of proteins changing, I'll say changing shape. So if you ever look at cottage cheese and you're like, ooh, that's disgusting. Well, kind of, but it's also kind of not. Because what it is a chemical change that has taken place to this milk um, to get it to basically change its state a little bit. So, with that in mind, when we think about chemical properties, well, we're over here. Chemical properties and some examples of chemical changes. If you have a bike and you leave it outside for the entire first semester of the year, what's going to happen is your bike chain's going to melt. Not melt, rust. Because iron metal is going to rust. If you eat a banana and you leave the peel outside, well, that peel is going to begin oxidizing. A green banana peel is going to turn yellow when it ripens. And then a dry piece of paper is going to burn. These are all chemical changes. So I want you guys to think about when it comes to physical changes, I want you to have kind of a vocabulary of words that you can think about as like, okay, that's a chemical change versus a physical change. So when it comes to physical changes, or sorry, when it comes to a chemical change, what I want you to think about is I want you to look for words like rust. So chemical changes. If something rusts, or this is a little bit more technical, and we'll get into this word later on, but oxidizes. If something oxidizes, well, that means a chemical change has taken place. Ripens, burns. Compare that to our physical properties and our physical changes. Gallium metal melts. Is melting, if something melts versus something burning, are those the same thing? No. If you take an ice cube and you put it out in the hot sun, is it going to burn? No. It's going to melt. So it's melting because it's changing from a solid to a liquid. When something burns, and one of the ways that I always like to think about this is solid goes to a liquid. If I were to take an ice cube, that's a solid, I can make it into, well, a puddle of water. Give me a number if you agree with that as a possibility. Okay. I didn't want to give the dissenting opinion. I didn't want to say, oh, if you disagree with that. Okay, so we can get an ice cube to melt into a puddle of water. Can we take a puddle of water and make it form a solid of some sort? Can we reform that ice cube? Yeah, absolutely. Now let's say that I get a tree and I light it on fire. It's going to make ash. Okay, so it burns. And could I get that ash? And Ryan and Kaylee have already responded to this. Could I take that ash and reform a tree? No. And somebody might be thinking, oh, but what if I planted that ash? No, I couldn't. Would it be used? Would it be a part of the carbon cycle? Sure. But I'm not going to be able to reform that tree in any functional fashion. Okay. Next up, physical changes. No bonds are broken or made. When an ice cube melts, the shape of the water changes, but it's still water. Another physical change is separating components of a mixture. I always think about this in the sense of like if you get salt water, salt water plus sand. Could I separate the sand out pretty easily? Yeah. If I had this mixture right here, I could separate that with filter it. And so if I filtered that, well, then I'd capture the sand, and then I'm left with salt water. Okay. Now, this is a pretty tricky question. And before you answer it, I want you to think about what happens if you got let's say, a Pyrex measuring glass with, the glass handle measuring cup. I'm not sure and you got some water in there. You put it on your stove and you heated it up. What's going to happen to the water in here where I put this X? It's going to evaporate, right? Nice. Okay. Now, what if I were to put like a top on this, kind of like a dome, and then I were to put, okay, so I've got this glass dome. I'm heating this up. Yep, pressure would build up. And then I've got an opening right here where I put this opening. Okay. Does everyone agree? Add a number to the chat if you agree that, well, this evaporating liquid is going to go up into here, into that dome that I've made. Would you agree with that? Add a number to the chat. Add a letter if you disagree with it. Okay. So you're right. This gas or this water that converts to a gas will float up into this dome. And what's going to happen is that, and let's say that it's 212 degrees Fahrenheit here. And then right here, let's say that it's 180 degrees, or let's change that arrow. Let's say right here, it's 180 degrees Fahrenheit. Right here. Is 180 degrees Fahrenheit cooler than 212? Yeah, it is. At 212, a liquid converts to a gas, or the liquid water evaporates. It converts from a liquid to a gas. What if it's below 212? Will it be converting to a gas? Like if you heat water to 212, aha, Kelly, you're absolutely right. Nicholas, you're absolutely right. It's going to go back. So I've got this gaseous water right here. It will float up, and then when it hits here, it's going to convert to a liquid. So if I heated this up from where this X is, goes into this dome, what's going to end up accumulating here? Where it's, let's say it's 30 degrees Fahrenheit. Or no, not 30. Let's say it's 80 degrees Fahrenheit. Absolutely. Water is going to accumulate there. Do you lose some quantity during this process? Kelly, that is a fantastic question. And the answer to that question is it kind of depends. Like this dome, if this is like a tight seal, no, you shouldn't. All of the water that's in here where this X is, it will evaporate. And then it will recondense, go from a gas back to a liquid here. Now, with that said, so this scenario that I had that I'm going to label A, I was doing it with just regular water. Can you give me a number in the chat if, okay, I agree, I follow you. And if you have any questions, please don't hesitate to, you can send me a private message or you can just send a public message. So now what I'm going to do is rather than go with pure water, let's say that I had SW or salt water. Salt water is a mixture. It's a solution. If I were to heat this, let's say that I went to, 212, 215 degrees Fahrenheit, whatever. Got it nice and warm in there. The water is going to evaporate. Give me a number in the chat if you agree with that statement. Okay. And let's say that I let this go for 1 hour. After an hour, after adding adequate heat, let's imagine that all the water is gone. All the water is now here, where I'm going to put a Z. And that cup Z, would you feel comfortable drinking that? Okay. My question is, if you're drinking that cup Z, are you going to be like, I don't like the taste of that? Well, no. You shouldn't really notice any taste difference because where is the salt going to be? The salt from the salt water is going to be here, where I've now put an X in the pan. You're absolutely right. This is a process, this is water desalinization or desalination. Now, this is also known as, or this desalinization or desalination is the removal of salt from salt water. So to make it drinkable. This technical process, if anyone's ever heard of any sort of like liquor or something like that, this is known as distillation. Distillation is a process that's commonly used for making like whiskey and other liquors, where, well, you're separating something based on its physical property, based on its boiling point. Okay, so my point here with respect to physical changes is we started out with a mixture, a complex mixture, salt water and sand. We removed the sand pretty easily because, the sand, we could have thrown it through a filter or a colander almost, like a really fine porous one. The salt water, on the other hand, it's like, oh, well, that's a solution. If you leave salt water just to sit for a week, ooh, that's going to be tough for that to separate. But if you add heat, well, the water will evaporate, the salt will not. Now you might be thinking, oh, but will the salt melt? So does table salt, can table salt melt? It can. The melting point for table salt is like 1,300 degrees Fahrenheit. So if we heat table salt to 212 degrees Fahrenheit, do we have to worry about table salt melting into a liquid? No, we're good. We don't have to worry about that. Table salt can melt, and if we get it that hot, it will. So my question for you guys is, what would you rather have poured on your hand? A, salt water, or actually, let me rephrase this. Um, is pouring liquid salt the same as pouring liquid salt water? Salt water. No. In order to have liquid salt, it's got to be like over 1,000 degrees. To have liquid salt water, that's at room temperature. One of those, if you pour it on your hand, like if you have an open cut, you'll be like, ooh, that stings. The other one, if it's poured on your hand, it'll be like, oh my gosh, my hand disappeared because it's over 1,000 degrees. I just stepped into a volcano sort of situation. Okay, so when a physical property or physical change has taken place, then we are talking about um, something that can be kind of undone, as opposed to bonds being broken or being made. Now, what I'm going to do is give everyone a poll question. This is poll question. It's about to pop up. Okay. Saving my question. And now I'm going to launch that question in the question. You should now see a question available to you. There's 100 people here. Okay. Keep this question going for a little while. Maybe about 10 more seconds. We've got 85 people who have answered. Oh, this is good. You guys are doing a great job. Great showing, everyone. 89. I wonder if we can make it to all 100. If we can make it to all 100, I'm going to put for 10 more seconds. 10 seconds. Got, I'm actually not going to put any stakes on it. 102.5. Okay, we got 5 more seconds. And I'm going to end the poll. Okay. So if you're using the if you are using a mobile device, sometimes what happens is the question pops up and you have to tap the screen and then it like switches around and you can see the poll question again. I will share the results for a little bit and you guys can see the results. My question of are the Bobcats going to win on Saturday? I'm impressed. I've been at Texas State since 2013. I was an undergraduate here in 2006 and before. I graduated in 2006. Um, School spirit during those days was like at an all-time, maybe not an all-time low, but I think if I posed this question in 2013, the response would have been, and what? Or it would have been Saturday? No? So this is great. This is a great showing. Um, we are. Absolutely. We are on the rise. So this is great. I hope that everyone who can go goes to the game. I'm going to stop the share of the question. Like I said last time, I'm going to have a couple of poll questions. So the first few days is just to like make sure that everyone has their system for answering the question. Um, since I got more than 90% response from the question, I'm going to give everyone a bonus point on their first exam. Um, so I'll make that note for myself. And in addition to that, everyone's going to get participation for these first few days as we're kind of making sure that everything's working. So, and just so you guys know, I that's one of the things that I like to do is just say like, hey, if we get, this level of participation, or if everyone gets it right, or if, this percentage gets it right, then bonus point. And most of the times, like I said, the stakes are not very high, so I'm not gonna be like anyway. Okay, so physical changes. Salt water or salt water in sand, we can separate those things. We have to use different techniques to do it. And with that in mind, I'd like you to think about to make this a class that's not solely Gen Chem light. Um, let's think about water desalination. Does the world have lots of salt water on it? Is there lots of salt water on the globe? Absolutely. What happens if you went out to, let's say you went to San Diego and you're like, oh, wow, this is so beautiful. I can just scoop my hand down and drink some water. And I'm going to do that every single day for the next week that I'm here. What's going to happen? You're probably going to get sick. You're probably going to start throwing up a lot. And if you continue to do it, yeah, chemical imbalance is going to could ultimately kill you. So salt water isn't good for people. So surviving on salt water isn't really an option. If you compare the amount of salt water that the earth has compared to pure water from water drinking sources that are safe, well, we don't have a lot of pure water sources. Are there pure water sources? Yeah. Texas, we've got access to lots of different aquifers and there's natural filtration there. But in terms of what we can do with that water, we don't really have many great options. So, or sorry, in terms of salt water. So, water desalination is a technology that is extremely important. And for some parts of the world, it's more important than others. But in addition to this being important, it's valuable. Like right now, if you were to go to a water desalination plant, chances are they're going to be basically doing this right here. They're going to be boiling that water to separate the pure water from the salt. Okay, great. Is that free? No. You got to have fuel to heat that water. You've got to have lots of fuel to heat that water to separate the water from the salt. And so that's not a free thing. So there's energy demands on that. And if there's an energy demand, there's a financial demand on that. So these physical properties, you might think like, oh, well, that's kind of simple, separating salt water from sand. Yeah, it is. It is pretty simple. And it's important. But to do it on a grand scale, it's very, excuse me, it's very expensive. Okay. Now, chemical changes. In a chemical change, bonds are broken and or formed between molecules or atoms. So in a chemical change, that's something where like milk curdles. Other indicators of a chemical change, well, it might change color. I mean, if you've let milk curdle, sometimes it gets a little bit yellow. Bubbles form because there's bacteria in that milk that have begun to ferment. And then maybe more than anything else, it's going to stink and it's going to taste awful. Now, this is not unique to milk. Um, if you've ever made kombucha, or if you've ever um, drank kombucha, well, it's got a unique smell and or taste. It's got some bubbles in it because, well, it relies on fermentation. If you've never had kombucha and you're like, ooh, I want to try that. Okay, I've had it. My wife and I used to make it, um, but it can get contaminated and that gets really gross. And then you basically just have to throw it away. Um, that was our experience, at least. So, yeah, chemical changes, these are what are taking place. Now, this one, light produced, that might seem like, well, that's how? I don't get that. That's tough to wrap my mind around. Well, when light is produced, one thing that I want you to think about is like fireflies. Fireflies. In order for a firefly's, I don't know what the structure is called, but in order for a light to be produced from a firefly, well, it is a chemical process that's taken place. And so a chemical reaction has taken place, a bond has been made or broken in order for that firefly to produce a small amount of light for that brief period. Okay. Now, give me a scale or on a scale of 1 to 5. 1 being good or great, whatever, and then 5 being not so good. Where do you, and you can send this as a private message, and this is totally optional. How do you feel about chemical properties, physical properties, chemical changes, physical changes? Okay. You saw an 8. It's outside of the. Um, Now, with that said, give me a Y or an N. Do you think that you could write your own multiple choice question about a physical or chemical change? And what I mean by that, the sort of question that you should expect would be something like, here's an example, like this thing has taken place. Is that an example of a chemical or a physical change? Okay, good. I'm seeing lots of yeses, so that's great. I think that's really one of the best ways that you can study for material in my class is to try to like write your own questions, write your own multiple choice questions, um, and share those with your peers. I know that I don't know if there's a group me for this class. If someone's made one, feel free to add the link to this chat. But to me, that's a very good way to communicate and say like, hey, here's a question, just sort of put it to the group. Okay, now next up, we're going to spend a little bit of time on this, and that is classification of matter. We've already talked about this a little bit, but we've got different states of matter: solids, liquids, and gases. Now, in some instances, you've probably heard of a fourth state of matter. Okay, yeah. I haven't seen anything about a group me. I think the discussion board, if the discussion board on our Canvas page isn't open yet, I will post that so then um, you guys can access that to, so I think, yeah, discussions, somebody can make a discussion, throw that on there, and that's a good thing to do. Then here's what I wanted to do was pull this up. Okay, so we've got our different states of matter: solids, liquids, and gases. That fourth state would be your fusion, and that's kind of outside the spectrum of this class. Um, the link at the top here is a nice little, we have a handful of different simulations over the course of the semester that we'll talk about, and they all come from this fet.colorado.edu. It's a really great resource for lots of different simulations. And usually the way that they're structured is they have kind of like here's the concept. Oh, perfect. Um, Ryan, if you actually, let me go ahead and I'll take a minute to pause my share, and then I will add this as an announcement. Class group me. 1310 group me. Okay. Um, I tend to not join the group me's. Um, so yeah. Okay. Resume. Okay, here we go. So there's always one simulation that's like, here's the concept and here's kind of the application. So if we look at this, states, we have on the right-hand side, atoms or molecules. We can select a substance. Let's just go with water. And then here, what we can do is adjust the temperature. So let's go ahead and go with degrees Celsius. So right now, this is water as a solid. It's negative 127 degrees Celsius. Now, if we were to heat this up, that temperature is going to continue to increase. What's kind of tricky about this is those water molecules, add to the chat, are they moving, Y or N? Yeah, they are. Your eyes are not, your mind's not playing tricks on you. Those are absolutely moving. Now, as we cool it down, what happens in their movements? Well, they slow down. So we heat it up, movement increases. Continue to heat it up, movement increases. Negative 32 degrees Celsius. Oh, and now we're at 5 degrees Celsius. Okay, so at 5 degrees Celsius, is this a liquid or is it a solid? Is it liquid water or solid water or gaseous water? At 5 degrees Celsius is actually a liquid because 0 degrees Celsius is the freezing point for water. So that this right here is a liquid. We cool it down to this would be a solid. Now, what I want to stress here, what I want you to take away from this is that regardless of the temperature, molecules are basically always moving. That's not to say you see that movement at like the macro scale. Because if you got an ice cube and you watched it in a freezer for a week, it's not like that ice cube is going to go from here to there. These are individual molecules. So the amount of movement is absolutely invisible to the naked eye. We heat it up, 17 degrees Celsius. We're going to go all the way to 66. We'll go all the way to 87. This is still a liquid. So at a positive from basically 0 all the way up to 100, our water is a liquid. When we go above 100, what has happened to our molecules? The number or the movement has increased. And now it's like they're floating away because here we have transitioned to a gaseous state. So these buttons on the side, solid at negative 127, yeah, water's a solid. When we click liquid, it's 13 degrees Celsius. Okay, the same is it's still gonna be a liquid at 18 or at 25. As a gas, oh man, the movement of those molecules is all over the map. So there's a relationship between the state of matter and the temperature. Now, this question up here, what type of property is a state? Add your response to the chat. Is it a physical or a chemical property? It's a physical. Yeah, great job. So it's a physical property because bonds aren't being made or broken. Because when we looked at this right here, and I'm going to pause it just so I can highlight one. When we look at this water molecule, that one right there, if I go to a liquid, no, well, I lost it. The molecule remains intact. The connections between molecules, those get disrupted, but the individual water molecules remain intact. So that would be an indication that we're talking about a physical change as opposed to a chemical change, or a physical property as opposed to a chemical property. Oh, now states of matter, they have different characteristics. So a solid, for instance, has a defined or a definite shape, has a defined or definitive volume. A liquid has an indefinite shape. And whenever you think about an indefinite shape, what I want you to think about is, let's say that I got my coffee mug here and I filled it halfway with water and I moved it, I sloshed it back and forth. The water inside this coffee mug is going, or the water in here is going to slosh back and forth. From whenever I hold it like this to this, the shape of that water is going to change. It's going to be a minor change. It's going to look a little bit different. It might even look like, oh, well, it's still water. Yeah, it is. But the shape of the water inside this mug has changed. The volume, however, the volume is going to remain the exact same. Meanwhile, a gas has an indefinite shape and an indefinite volume. Now, I have a tendency to tell stories, and I hope that you know how good these stories are. But whenever I was in sixth grade, it was one of the most spectacular days I ever had. It was when one girl brought a stink bomb to class. And I don't know if anyone's ever seen a stink bomb, but they were little glass vials. And they had like this solution inside of them. And she took it into the bathroom and she smashed it in half. There's a liquid that was contained in there. And that liquid, well, it aerosolized. That liquid converted to a gas. So that liquid, well, it was confined to that container. Whenever that glass container was broken, then that liquid converted to a gas. Now, all of a sudden, that gas is going to fill the bathroom. All of the space in the bathroom is the new container. So the volume that liquid was in has increased dramatically, or that because it changed to a different shape, or it changed to a different state. So that gas filled the bathroom. Then that gas filled the ducts. And that duct work went throughout the entire school. So eventually that gas, that smelly gas, filled the entire school. And it was a spectacular day in sixth grade because what happened? We got sent home early. It was really fantastic. And it all had to do with a physical property. That gas filled the bathroom, then it filled the bathroom plus the ductwork, then it filled the bathroom plus the ductwork plus the entire school. So what did they do? Well, they opened the doors. And now all of a sudden that gas filled the entire atmosphere. And so this physical property of having no defined shape and no defined volume helped some kids go home from school early a little bit. And it was wonderful. Okay. Um, it was. It was insane and it was awesome. Thank you very much for the feedback on that fantastic story. Okay. So solids, liquids, and gases. These are different property, or these are different characteristics of them. Now, types of matter. Everything, every type of matter is going to fall into two different categories. It's either going to be a mixture or it's going to be a substance. A mixture is composed of two or more substances, whereas a substance is either going to be an element or a compound. Now let's take this avenue on the left-hand side. A substance is either going to be an element or it's going to be a compound. Now, water is an example of a compound. And an element would be something like pure gold. So you could make a mixture of gold water. Cool. And from that mixture of gold water, you could separate out the pure gold and the compound known as water. Now, gold is a metal known as Au. Now, thinking about gold water, if you had like, let me ask you this. Add a Y or an N to the chat. Do you think that gold is soluble in water? Y or N? No. So when something is insoluble, like gold water, is that going to make an A homogeneous solution or a B heterogeneous mixture? A heterogeneous mixture is where you can see the separate parts. A homogeneous mixture would be something like milk. Milk is a homogeneous mixture. It's a mixture of proteins, fats, and sugars. So you're absolutely right. If you made gold water, where you had water with a bunch of gold flecks in it, yeah, B, it's a heterogeneous mixture because those gold uh, flakes, you're going to be able to pick those out. Okay. Now, elements versus compounds, we got this slide and one more. An element is composed of one type of atom. A compound is composed of two or more atoms or elements. So here an element is going to either exist as gold Au, which is just a bunch of these atoms assembled together, or oxygen, O2. Two oxygen atoms come together to make O2 that's breathable for us. A compound, by comparison, is two or more elements. It's either water, H, or two H's and one O, or table salt, which is Na and Cl. An atom is your smallest characteristic part of an element, and a molecule is composed of two or more atoms. So a molecule of water, a molecule of carbon dioxide, a molecule of O2. So what's a little bit tricky here is O2 can exist as a molecule of multiple elements, of two oxygen elements. So it's two oxygen atoms that come together to make a molecule. Okay, that's where we're going to stop today. I think we'll probably pick up with this slide on Tuesday, just so we can kind of like fold this into Tuesday stuff. Thank you guys very much for coming to class. Thank you guys for your participation. I appreciate it. We got a bonus point on exam number one from that feedback that we did, or that quick response that everyone gave. Where do we do our homeworks and quizzes? I will post an announcement whenever the first ones are up. I haven't posted anything yet, but I'll give you a rundown, or the description will have the rundown of this is what you need to submit and how you need to submit and dates and everything like that. Other than that, though, I hope that you guys have a great Thursday, have a great Friday. If you go to the football game on Saturday, have fun, be safe, drink lots of water, wear a big hat, sunscreen, all the safe things. Deal? The syllabus and Tuesday's recording will be posted a little bit later today, along with today's recording. Kieran, I will post the Zoom recording later today. It will be on that same. They're always going to be on the default page for our class. Yes, they will. No homework has been posted yet. I gotta stop my recording now.